Hi everyone, I hope you're all doing well and in good health. In video 13, we explained the vanishing gradient problem in simple terms, avoiding complex math. Video 14 explains the vanishing gradient problem step by step using mathematical concept. In this video, we will take a detailed look at the causes, consequences, identification methods, and possible solutions to this problem. Let's start from causes of the vanishing gradient problem. There are two major causes of vanishing gradient problem: activation functions and depth of a neural network. This figure shows how the vanishing gradient problem arises within a neural network by activation functions like sigmoid and tan. When inputs are either very large or very small, it often leads to very small gradients during backpropagation. These small gradients are insufficient to update the weights of the earlier layers effectively. As a result, the vanishing gradient problem occurs. Depth of the neural network may also cause vanishing gradient problem. In networks with large number of layers or several neurons, gradients must pass through many layers, and repeated multiplication of small derivatives can cause them to vanish. Now let's talk about its consequences. We use a deep neural network to illustrate the consequences of the vanishing gradient problem. Let's see what's happened actually. During backward pass on early layers, gradients become very small as they move backward through the layers. This results in minimal or no weight updates in the earlier layers. So, first, it leads to slow learning in the early layers. These layers are crucial because they capture the basic features in the data, but with gradients too small to update their weights, they stay stuck. Second, training can become stalled. The network gets stuck in poor solutions, like local minima or flat regions of the loss surface, and can't move forward. As a result, it fails to converge to the best possible solution. And finally, when early layers stop learning, the network loses its ability to understand deeper and more complex patterns in the data. So, while the vanishing gradient might seem like a small technical issue, it can actually bring the entire training process to a halt. In this section, we will explore two examples to help identify the vanishing gradient problem. In the first case, observe this figure generated using Keras, a deep learning library. It shows the training progress of a model over 100 iterations, known as epochs. Despite repeated training, the loss remains nearly constant, and the accuracy stays around 51%, which is close to random guessing. This lack of improvement strongly suggests that the model is not learning effectively, a common indication of the vanishing gradient problem. In the second case, we examine a graph showing the relationship between weight values and training epoch. As illustrated, the weights in the neural network remain nearly constant throughout the 50 training epoch. In a normal learning process, these weights should change significantly as the model learns from the data. However, the flat lines indicate that the weights are barely updating, which is a typical sign of the vanishing gradient problem. This occurs when the gradients become too small to drive meaningful updates, causing the model to stagnate early in training and preventing it from learning effectively. Now it is the time to discuss solutions of gradient vanishing problem. It can be effectively mitigated through several strategies. Rectified linear unit and its variants, for example, leaky ReLU, parametric ReLU, prevent gradient saturation by allowing positive activations to pass unchanged, ensuring non-zero gradients during backpropagation. Reducing the number of layers or neurons simplifies the network, decreasing the multiplicative effect of small gradients across many layers. Batch normalization stabilizes and accelerates training by normalizing layer inputs, helping maintain stronger gradient flow. Residual networks introduce skip connections that bypass layers, enabling gradients to propagate directly and mitigating degradation in deep network. For sequential data, long short-term memory networks address vanishing gradient problem in recurrent neural networks through gating mechanisms that regulate information flow, preserving gradient strength over long sequences. Together, these techniques enhance the trainability of deep neural networks by maintaining robust gradient signals throughout the learning process. That wraps up today's video. Please don't forget to subscribe our channel, like the video, share and comment it to stay updated with this series.